Hidden near the very edge of what we can observe, tucked behind a wall of closer galaxies, sits an object that has no business existing. Not because it behaves strangely, and not because it poses any danger to anything, but because, according to everything scientists thought they understood about how the universe assembled itself, there simply wasn't enough time for something like it to form. When astronomers first turned the James Webb Space Telescope toward the earliest few 100 million years of cosmic history, they expected to find a beginning. Small, messy, half-formed clumps of gas, still figuring out how to become galaxies. Instead, they found something that already looked finished. A black hole so massive and so absurdly early that it doesn't fit inside any accepted timeline of cosmic history. That discovery is a few years old now, but the story around it is very much still unfolding, including a genuinely important twist that only landed this past June. To understand why this counts as a real scientific crisis, rather than just a curiosity, you need to understand exactly which rule it breaks. A black hole isn't supposed to be born large. In the standard story of cosmic history, the first black holes started as seeds. When the earliest generation of enormous stars finally burned through their fuel and collapsed under their own weight, they left behind dense cores weighing perhaps a few hundred times the mass of our sun. Small by cosmic standards, almost trivial in the grand scheme of things. From there, a black hole has only one way to grow. It feeds. Surrounding gas spirals inward. Friction heats that gas to millions of degrees, and the black hole slowly packs on mass over unimaginably long stretches of time. But there's a genuine speed limit built into that feeding process, and it isn't a flexible guideline. It's baked directly into physics itself. As gas falls toward a black hole, it glows so intensely that the outward pressure of its own radiation starts shoving away the next mouthful of gas trying to fall in behind it. The harder a black hole tries to eat, the more forcefully it ends up pushing its own food away. Astronomers call this the Eddington limit, and for decades it has functioned like a built-in governor on an engine, capping how quickly any black hole can realistically gain weight before choking on its own light. Run the arithmetic from a seed weighing a few hundred suns, feeding at the absolute fastest rate physics normally allows, with zero interruptions, and reaching the scale of the true monsters sitting at the centers of galaxies, today should require billions of uninterrupted years of steady growth. The early universe simply didn't have billions of years to hand out. The object that first cracked this story wide open carries a deceptively plain name, UHZ1. Finding it at all required borrowing a trick from nature itself. A massive foreground cluster of galaxies known as Abell 2744, nicknamed Pandora's Cluster, sits directly between us and the deep, distant universe. Its gravity is so immense that it physically bends the fabric of space around it, warping and magnifying the light of anything sitting directly behind it. From our point of view, the entire cluster becomes an accidental lens, a telescope the size of a galaxy cluster built entirely out of gravity, pointed straight at the dawn of time. Peering through that natural lens, the James Webb Space Telescope picked up a faint smudge of infrared light back in 2023. Meanwhile, NASA's Chandra X-ray Observatory, staring at that exact patch of sky for more than 2 straight weeks, caught something else entirely. A burst of X-rays, the unmistakable signature of superheated gas being violently torn apart as it spirals into a black hole. 2 completely different telescopes, 2 entirely different kinds of light, one object sitting at the center of both. That X-ray signal was so faint that Chandra should never have detected it at all under normal circumstances. It only became visible because the gravitational lens amplified the signal roughly 4-fold. Without that lucky cosmic alignment, this discovery simply never happens. When researchers first measured the distance involved in the paper led by Akos Bogdan of the Harvard-Smithsonian Center for Astrophysics and Andy Goulding of Princeton, published in Nature Astronomy in late 2023, the number was staggering. Light from UHZ1 left its home galaxy roughly 470 million years after the Big Bang, at a redshift of about 10. And that light has been traveling for more than 13 billion years just to reach us, covering a distance of about 13.2 billion light years. We're looking at this galaxy exactly as it existed when the universe was only about 3% of its current age. We have no idea what it looks like today. We're looking at a photograph of the universe's infancy that took 13 billion years just to arrive in our mailbox. Then researchers weighed it, and the number that came back was even harder to explain. Estimates placed the black hole's mass somewhere between 10 million and 100 million times the mass of our sun, assuming it was accreting near the Eddington limit. Not a seed, not a leftover stellar remnant, but a fully grown supermassive black hole already actively feeding, while the rest of the universe was still figuring out how to produce its first light. Raw size alone isn't really what makes this such a deep problem, though. The real issue is the ratio. In the universe around us today, there's a remarkably consistent relationship between any given galaxy and the black hole at its center. Add up every star inside a typical modern galaxy, and their combined mass usually outweighs the central black hole by roughly a factor of 1,000. The black hole normally amounts to something like 0.1% of the total, a tiny seed buried deep inside an enormous piece of fruit. Inside UH-1, that relationship collapses entirely. The black hole isn't a rounding error at all. Its mass turns out to be roughly comparable to every star in its host galaxy combined, according to the original discovery paper. It's as though the seed had somehow grown to weigh as much as the entire fruit surrounding it. That mismatch is exactly why astronomers reached for a blunt label for objects like this. Overmassive black holes simply too large for the galaxies supposedly containing them. If UHZ1 were the only object like this ever found, this story would be little more than a curious footnote. It's nowhere close to being alone. As the James Webb Space Telescope kept scanning deeper into the young universe, it kept turning up more of them. Astronomers eventually identified an entire population of faint, tiny, deeply red points of light scattered across the early cosmos, so compact and uniformly crimson that researchers nicknamed them little red dots. These objects show up in large numbers starting around 600 million years after the Big Bang, and then largely vanish from view by roughly 1.6 billion years after it, a surprisingly narrow window in cosmic terms. Their spectra carry a distinctive shape unlike almost anything else observed in the sky. Bright in ultraviolet light, bright again in optical light, but strangely dim in the narrow band between the two, forming a rough V shape that immediately caught observers' attention. On top of that dip, many show broad emission lines typically associated with gas swirling rapidly around an active black hole, while at the same time showing conspicuously weak or absent X-ray and radio emission, exactly the kind of signal astronomers would normally expect a genuine black hole to produce. That contradiction, strong optical evidence for a black hole paired with almost no confirming X-ray signal, is part of what made this population so difficult to classify from the beginning. Look closely at many little red dots, and you find strong evidence of a heavy black hole at the center, far heavier than its tiny host. The galaxy should reasonably be able to support. In the most extreme individual cases, some show 10, 20, occasionally as much as 30% of the entire galaxy's mass concentrated in that one central object. One brilliant quasar, cataloged as J0313-1806, shining out to us from roughly 670 million years after the Big Bang, is powered by a black hole exceeding 6 billion times the mass of our Sun, fully assembled inside a universe that had barely gotten started. At this point, the real question stopped being whether one single black hole somehow managed to grow too fast. The real question became how an entire generation of them managed to do it at the same time. There are a handful of possible explanations, and everyone would rewrite part of the accepted story of how the early universe built itself. One leading explanation has been that these black holes never began as small seeds at all. Rather than patiently waiting for a massive star to be born, live out its life, and eventually die, an enormous cloud of raw primordial gas may have collapsed directly into a black hole in one catastrophic event. No intermediate stellar stage required, starting not at a modest few hundred suns, but at a heavy seed weighing somewhere between 10,000 and 100,000 suns. A second possibility holds that the speed limit itself isn't quite as strict as physicists once assumed, that inside the dense, chaotic hearts of the first galaxies, a black hole might occasionally feed far faster than the standard Eddington rate technically allows, gorging itself in short, violent bursts that temporarily overwhelm its own radiation pressure and let it briefly race ahead of the clock. But there's a third possibility, and this is the one that has genuinely turned this story from a settled discovery into an active, ongoing scientific argument playing out in real time. Astronomers can't see these black holes directly. Every mass estimate is inferred indirectly from the light coming from gas swirling around the black hole and how fast that gas appears to be moving. And every one of those measurements depends on a chain of assumptions that has to survive an unbroken 13 billion year journey before it reaches our telescopes. Over the past couple of years, several research teams have started seriously questioning whether these particular measurements can even be trusted at such an extreme distance. That skepticism reached a real turning point this year. Back in January 2026, astronomers presented findings at a major astronomy conference suggesting that at least some little red dots might actually be enormous, extremely short-lived stars, rather than black holes wrapped in gas at all, essentially a direct observable snapshot of the exact stage where a massive star's collapse gives birth to a black hole seed. Then, in June 2026, a team led by astronomer Vasily Kokorev at the University of Texas at Austin published the most detailed spectrum ever captured of a single little red dot, an object gravitationally lensed behind the galaxy cluster Abell S1063 and cataloged as Glimpse 117 Spelem 5, seen as it existed roughly 1.8 billion years after the Big Bang at a redshift of 3.5. Webb captured a 30-hour spectrum of the object, and the gravitational lensing effectively stretched that into the equivalent of 80 hours of telescope time, an incredibly lucky combination that pulled out more than 40 distinct spectral lines, the richest set ever gathered from an object like this published in the Astrophysical Journal. Every one of those 40-plus lines pointed toward a related but distinct conclusion from the January proposal. Rather than being straightforward supermassive black holes shining in the open or purely transitional stars, these objects appear to be young supermassive black holes wrapped inside incredibly dense cocoons of ionized gas. Inside those cocoons, a process called electron scattering, rather than gas simply orbiting at extreme speed, is what broadens their light signatures so dramatically. Once researchers accounted for that scattering effect, the black hole mass implied by the data for GLIMPS 1.2075 dropped substantially compared to earlier assumptions, landing around 5 million solar masses rather than the far larger figures some earlier cruder estimates might have implied for objects like it. Researchers have started calling this the black hole star model, and Kokorev himself put the significance plainly, saying part of the scientific community is converging on this single picture, though he noted that no previous little red dot had all the pieces of evidence lined up in one place the way GLIMPS 1.775 did. That finding genuinely matters, because for roughly 4 years, plenty of astronomers had openly worried that little red dots represented a fundamental crack running through modern cosmology, with some going so far as to say the discoveries had broken cosmology. This new spectral evidence suggests that, for at least a meaningful portion of this population, the universe was never actually broken in the way it first appeared. Our measuring instruments were being fooled by an unusual physical disguise nobody had previously accounted for. Dense gas clouds mimicking the appearance of impossibly heavy black holes. Here's where things get genuinely complicated, though, and where the story refuses to wrap up into one tidy conclusion. UHZ1 itself was never actually one of the little red dots swept up in this same spectral reanalysis. Its mass estimate came from a fundamentally different measurement technique entirely, built directly from Chandra's independent X-ray detection rather than from the broadened emission line spectroscopy driving the newer black hole star model. That means the reanalysis resolving many little red dot cases in 2026 doesn't automatically resolve UHZ1's own extreme mass problem in the same stroke. Its X-ray signature still points toward an actively accreting black hole holding real weight, and its position sitting right alongside its tiny host galaxy at such an early cosmic moment remains a genuine unresolved puzzle even after this year's breakthrough. Part of the original overmassive black hole crisis may be quietly resolving itself as better data comes in, while another part of it, including the very object that originally kicked off this entire conversation, still stands largely unexplained. So the field currently finds itself split roughly 3 ways. Some objects likely represent black holes that were simply born unusually heavy from the start, through direct collapse. Some likely represent black holes that briefly broke past their theoretical speed limit during rare, violent feeding bursts. And some, quite possibly a meaningful share of the original little red dot population, may never have been quite as impossibly massive as they first appeared, once astronomers properly accounted for the dense gas clouds disguising them. Untangling exactly which explanation applies to which specific object remains one of the most actively contested questions in observational cosmology heading into the second half of this decade. That uncertainty is precisely what keeps a discovery like UHZ1 from becoming just another entry on a list of cosmic record holders. Because if objects like it are exactly as massive as the current X-ray evidence suggests, the basic order of cosmic creation may genuinely run backward from everything astronomers originally assumed. The standard picture always had galaxies forming first, slowly gathering gas and stars, with a black hole growing gradually inside that structure, almost like something raised patiently by a parent. But a genuinely overmassive black hole hints at the opposite arrangement, that the black hole itself came first, and the surrounding galaxy assembled around that central darkness afterward, the seed, in a very real sense, growing the fruit around itself rather than the other way around. It's worth pausing on just how quickly this entire field has been forced to correct itself, because that pace is unusual, even by the standards of modern astrophysics. Little red dots were first noticed in Webb's earliest images back in the summer of 2022, barely visible smudges nobody had a name for yet. Within 2 years, they had become one of the most argued over populations in the entire sky, with some researchers calling them evidence of broken cosmology, and others insisting they represented perfectly ordinary physics, dressed up in an unfamiliar disguise. By January of this year, teams were presenting evidence that at least some of these objects might actually be enormous, short-lived stars rather than black holes at all. Just months later, the June 2026 spectral analysis pushed the leading interpretation back toward black holes again, just smaller and better disguised ones than first assumed. That kind of whiplash, 3 or 4 competing explanations, rising and falling within a single stretch of years, is exactly what real science looks like when it runs into genuinely new territory, with no existing playbook to follow. What happens next largely depends on more telescope time and more gravitational accidents, exactly like the one that revealed UHZ1 in the first place and the one that made Glimpse 17775's spectrum possible. Additional lensing clusters are already being surveyed specifically in search of more of these extreme early black holes, and instruments designed to detect fainter X-ray sources may eventually help settle whether objects like UHZ1 represent a rare extreme edge case or an entire hidden population still waiting to be uncovered. Until that evidence arrives, the honest answer is that nobody fully knows yet whether the universe quietly broke one of its own rules just once near the very beginning, or whether it has been doing this all along in places we simply haven't looked closely enough to notice. 13 billion years ago, in a universe that had barely learned how to produce its first light, something sitting in the darkness was apparently already enormous. We only caught its shadow by accident, bent and magnified through the gravity of an entirely unrelated galaxy cluster, sitting right at the limit of what our instruments can detect. And even now, with sharper spectra, competing theoretical models, and a genuinely important correction to part of this story landing just this year, astronomers still can't fully explain how something like UHZ1 got there so early, or so heavy in the first place.